All right. So I'll just continue with our lecture last time. Um, we basically introduced the rationale of using linear model, right? We said it's good for its interpretability, and also it has very good numerical, I would say, closed form formula, which will make the computation even feasible before we had computers. So that was a big achievement back then. But for now, even though we have computers, even GPUs to allow us to do very large model training, but if we really care about understanding a certain parameter in the model, then at least for that parameter, we need to specify in the way that we can understand. And in linear model, it is good that every parameter has its meaning and are interpretable. So let me just try to go back to where we stopped last time. We basically introduced the matrix form of linear model. Let me see. Matrix form of linear model. And we introduced the response y as n-dimensional vector, right? And we have x as the design matrix response and x as the design matrix, which we specify it to be n by p. But please note that in this class, we consider the first column to be just of ones for the intercept. And then we have predictors x1 to xp minus 1, p of them, p minus 1 of them. That will give me an n by p design matrix. And I would have a coefficient vector, which I will put here, beta is p-dimensional, which will be the intercept as the first entry, and then p minus 1 predictor's effect. And finally, we will have the error vector, which is n-dimensional. So this is what we assume to be the error or randomness or noise, whatever you call it, that cannot be explained by the model. So we will decompose the y, the response, into two parts. This is the matrix form. X times beta plus epsilon. So each part is n-dimensional. So what x beta does is that it tries to explain part of the response we observed, and it's what we are interested in, because the explained part can basically be explained by the predictors, and that's what we try to infer, right? What are the effects or effect sizes of the predictors on the response? But we also know that our data is not perfect, so this error term is just here to tolerate the part we don't explain. So one question I received from the last lecture is about this random design versus fixed design difference, which I will elaborate a little more today. So when we say random design or fixed design, we are talking about X. So please note that in this matrix form, we are stacking the n observations we get into this form, right? So we already have n observations from some population. So X as a design matrix has n rows. So if I write it out, I would just write it as x1 transpose to xn transpose, okay? So this is what we said last time. It is, for each row, it is the observation, p-dimensional observations, with first one as 1 intercept and the rest p minus 1 as the predictor values. So when we say fixed design, which is often the case in the field, people call experimental design. I don't know how many of you have taken a class of experimental design before, but this is actually where statistics started as a discipline. That is, for example, if I want to design my experiment about a drug effect, then my predictor would be the drug dosage. And I can design specific concentrations or dosages for this drug. And at each dosage, I'm going to measure the, how to say, maybe some drug activity or effectiveness. So the drug activity will be my Y, and one predictor will be my drug dosage. Since in this case, experiment is what I designed, then the values of X is pre-specified. So before I even collect the data, I already lay out the design matrix. So I have this matrix already, based on which I do the experiment, I collect the Y. And that is where the fixed design was originated from. So in this case, even though someone else will might repeat the experiment, but in this case, the design matrix will stay the same. With the same design matrix, just different measurements of Y. So that's why in the fixed design, we only consider randomness in the error term or the unobserved term, but and then measure the Y, right? So the Y's are different, but X is the same. So in this case, it does not, we don't have any reason to believe that X is random. But what is a random design? It's often applied to the so-called observational study, which means that the data is just a random observation. For example, if we do a survey, then we cannot control who are the people we can ask questions for. So then the people in our survey are a random sample from the human population. So in this case, when we do the survey again and we ask a different group of people, then the X matrix will be different, right? Because their predictor values will be different. So in this case, it's more reasonable to assume that X differs from study to study, from sample to sample. So therefore, it does not make sense to consider it as fixed. So basically, that's where the difference comes from. So if we use the terminology of random variables or random vectors, so in the random design, we would need the joint distribution of X and epsilon. So if we want to write about the likelihood, for example, we need to be based on the joint distribution of X and epsilon. But for the fixed design, it is only the distribution of epsilon, because epsilon is the only random vector in the whole model. So that's the big difference. But what consequence does this have for our inference of beta? Because beta is our parameter of interest, the effects of the coefficients we're interested in. So what influence does this consideration, fixed design versus random design, how would that affect the inference for beta? That is a question we'll see later. Okay, so let's continue with the likelihood we wrote last time, if you recall. So we said that under the model, and in statistics, the model we talk about are probabilistic models, which involve random variables. And here in the fixed design, it's the epsilon. Okay, so let me just say fixed design. So if we just assume that epsilon as an n-dimensional vector follows an n-dimensional Gaussian distribution with a mean 0, and for multivariate Gaussian, we talk about variance covariance matrix, right? Because we have n items, n random variables here. So we need to consider what is each one's variance, what are their pairwise covariances. But here we make it simple. We just assume that sigma square, a scalar times identity matrix, which means that we're assuming all the error terms have the same variance sigma squared and they are uncorrelated. Under Gaussian, they are basically independent. So in this case, we should just call this, we have this assumption, okay, this common sigma, if they are common for all epsilon i's, for all the errors, this is called homoscedasticity. It's a very long term. Some of you might have seen this term, but when people use this term, it means the common sigma. And in contrast to this, on the contrary, you can say heteroscedasticity. In that case, it means that each epsilon I can have its own sigma I, which is something we will talk a little bit later. Okay, so under this very simple but strong assumption, we have an easy way to write down the likelihood, which is what we did last time. So the likelihood of beta, for beta, I should say likelihood of beta, yeah, a function of beta. So it is a function of beta, and it's about the likelihood of observing our sample given a particular beta value. So last time we wrote that big L for likelihood. So it's basically this, based on simple Gaussian density function, exponential negative 2 sigma square. Here's a sum, I from 1 to n, yi minus xi transpose beta square, right? This is what we wrote last time. And then we said, oh, the numerator in the exponent, this one, can actually be written in the matrix form. So we said that basically this sum, I'll just write it again, yi minus xi transpose beta squared. We just did a little derivation on the board last time, can be written as y minus x beta transpose times y minus x beta. Okay, so with this, then we said at the end of the class last time on Monday is that if we want to find the beta value that maximizes the likelihood, we call this argmax. It is basically the same beta value that minimizes this term because in the exponent, we have a negative sign here. So this is basically equal to the argmin of this term, y minus x beta transpose y minus x beta. It's the same beta value. So if we consider the left to be our parameter estimation objective function, we can say that we are basically doing MLE, maximum likelihood estimation, to find the beta estimate. If we use the right-hand side as our objective function to minimize, we can say that we're doing OLS, which is ordinary least squares. So under the fixed design, the interesting thing is that they happen to be the same estimate. They will give us the same beta hat. But under the random design, it's not as simple because, as I mentioned, if you want to write out the likelihood function for beta under the random design, then you must consider whatever distribution the design, the features, the predictors, the x takes, right? But we don't have that information assumed in the fixed design. We just assume for epsilon, because we treat x as determined, as fixed. Okay, I hope this makes sense to you. And one more way to write this, you will also see it's just the same as this one. You will see it in some literature text, is that people may write this as this, y minus x beta. So what this means is that it's the square of the L2 norm. Okay, L2 norm is what? It's basically the square root of this. It's the L2 norm of a vector. So we basically have, so if we have a vector, I will say just for y, for example. So for y, the L2 norm is basically square root of the sum of yi squared. Okay, that's the L2 norm. And L1 norm, which is also commonly used, is the sum of the absolute values of yi. Okay, and if we say infinity norm, we mean the the max of the absolute value. So these are the most commonly used norm, but L2 norm square is basically this. Okay. All right, so then the next question is, how do we solve this optimization problem? How do we find the beta value? So in this case, once we have the vector form, we can use vector calculus to help us do this. So we basically just want to take a gradient against the vector beta, okay? So what we want to do is that d beta of this y minus x beta transpose y minus x beta. Okay, and last time we give you the expanded form for this product, which is y transpose y minus 2 times y transpose x beta plus beta transpose x beta, right? And I think we have two, yeah, I think that's it, basically. This is expanded form. And then when we take the gradient against beta, we will just follow some rules in vector calculus. The first term does not involve beta, so it can go away. The second term involves only one beta, and beta is being right multiplied. So we just keep the left part to be in the gradient. So we have negative 2 y transpose x. Let me see if the gradient is correct. Okay, so this is a tricky thing. We will try to define the gradient as column gradient, not row gradient, because of that convention I'm trying to follow. So then this will be x, y transpose. Okay, so then this will be p by 1. So we can keep it as a column gradient. Shouldn't the arcmean be beta? So there's a common, shouldn't the arcmean beta be x transpose beta? X transpose B? What is B?
Sorry, from the look of the notation, I think that the arcmean beta expression should be y minus x transpose beta multiplied by y
Which
minus
line are you talking about?
arcmean beta
This
p
one?
of s. Yes.
I'm not doing anything. I'm just trying to expand this one and then take the gradient.
Yes.
And then your comment is, are you saying that there is a solution answer you can see out of it, or what's your comment about? Because I'm
Uh
trying to derive what's the argument.
oh, I see. Yeah, my apologies.
Okay, thank you. Okay, so we're trying to get the gradient of this term of this objective function and set it to 0 to solve for the argument. That's what we're doing right now. Okay, so this is the first term after taking the gradient. And for the second term, once we take the gradient, just like in the scalar form, this is like a square. When we take the square, take the derivative of a square, there will be a 2 coming out of it, right? So the same thing applies here. So there will be a 2 coming out of it, and we want to keep it as a column vector. So this will turn out to be 2 times x transpose x beta. That's it. So in the second term of the gradient, we keep 1 beta. And we will set this gradient to 0 to optimize. So to try to find the minimizer, the argument.
Sorry, Professor.
Yeah.
I feel like XY transpose is wrong.
Oh, sorry. No, x y transpose is p by 1 because sorry. Okay, I think this is something what I'm trying to think. X y transpose. Let me see. Sorry, it's a typo. Yeah, what I had in mind is x transpose y. That's what I want to say. Yeah, sorry. Yeah, x transpose y is p by 1, and you can also check the second term is p by 1. So it's important to check that the dimensions are correct. All right, so then to set this gradient to 0, it becomes what? It becomes, we just move 1 to the right-hand side, so it becomes just x transpose x beta is said to be equal to x transpose y. That's the thing. That's the thing we want to solve for the estimate of beta. And this equation is famous in linear model. It has a name called normal equation. Okay. And I think the normal, it could come from normal distribution, we assume for epsilon, or it could also mean that something that's very important for this whole problem. And if we solve for this, right, then essentially we just need to multiply the inverse of this matrix if this matrix is invertible. And this matrix, just for information, is P by P. Okay, so we will just have P hat equals to X transpose X inverse X transpose Y. So this is the thing we will use again and again, which is the OLS formula for beta estimate. And as I already said, to require this X transpose X to be invertible, based on our knowledge of linear algebra, since X is n by P, right? And this is P by P. To make this invertible, we cannot have P larger than n. If P is larger than n, this cannot be. So P must be less or equal than n. This is something we require. Beyond that, this is not sufficient. We also need that the columns of X are linearly independent. So this independence is not the probabilistic independence, but it's the linear algebra independence. So what this means is that there's no column in X that can be written as a linear combination of other columns. Otherwise, you will have the column rank of X less than P. And then as a result, this rank of X transpose X will be less than P. So it won't be invertible. So basically what we're saying here is that it's P less than N and X has column rank of P. So we need both. But I know that in some cases, people may say, oh, I can do a pseudo inverse if there's not a real inverse, but that's a separate question. Okay, so, and then because of this estimation problem, when P is larger than N, sometimes people would need to pose some constraints or regularization to make this estimate stable. And that is another topic, big topic itself, called sparse estimation for high dimensional linear model. So for example, the lasso method, the most famous one for solving this problem, was developed for that purpose. And the related one is the ridge regression. So we'll see if we have some time to briefly talk about them. But in this classical simple case, when you have predictors that are not so many, then this invertibility problem is not an issue. Okay, so for now, this is the most important formula we have introduced. What is beta hat? Because beta is our parameter of interest. So then, as I introduced in our last lecture, statistics, a large part of it focuses on inference. And inference is about how well do we think our parameter estimate can inform us of the parameter, right? So what can we learn from the parameter estimate? So then we are interested in studying properties of this parameter estimate. Okay, so there are certain properties we often consider when we study an estimator because it's related to the story we want to tell. So the first one we often consider is whether it's biased or not, the bias of an estimate. So what does that mean? It means that we are taking the expectation of the estimate. Again, this is under the frequentist paradigm I introduced last time. So when we say estimation, when we say expectation, we are talking about average, the average over all possible repetitive samples. So not just the sample we observe, but all potential samples coming from the same distribution. And we're looking at that average, and we call that expectation. So it's an imaginary thing in our mind. But what this means is that suppose we can repeat our experiments for infinite number of times, will we get the truth by averaging? So that's why the bias is about how well the estimator is in capturing the truth. Because if it's good, then we hope as long as we have the resource to repeat experiments for many times, then the average will get us closer to the truth. So that's why bias is defined as expectation minus the true value. Okay, and now we're going to, when we talk about expectation, the first thing to think about is what random variables are we taking expectation over? to consider. And here we plug in this formula for beta hat. It's expectation of x transpose x inverse x transpose y minus beta. Okay, and in this one, the only random variable is the y, because y is random because epsilon is random. And in the fixed design, the reason I said it's simpler, it makes something simpler because we don't need to assume its distribution. We just treat it as fixed and we can move it out of the expectation since it's fixed. So it's basically x transpose x inverse x transpose expectation of y, okay, minus beta. Okay, now the question is, what is expectation of y? And if we come back to the model here, under this model, we just assume epsilon has mean 0, x beta is a fixed term. So basically, expectation of y would just be x beta because expectation of epsilon is 0. Okay, so then we would actually find this to be equal to x beta. Then you see we can have some cancellation. X transpose X inverse can be canceled with this X transpose X following it. So we get beta. So it's basically beta minus beta, and that's 0. So this is the bias calculation. And we can conclude that under the fixed design, beta hat is an unbiased estimator. So that's the first property we can say for this beta hat OLS estimate. Okay, the second property after bias is variance. Okay, so I would say if you think about statistics, the bias variance trade-off is the most important property I would say that we should always consider. So bias is whether you can have the good average if you repeat your sampling for infinite number of times. But there could be very big variability from sample to sample, right? So from each sample, your parameter estimate can be very different, even though if you can aggregate them by averaging, the average is close to the truth, is the truth. So bias cannot reflect how reliable, still cannot fully reflect how reliable the estimate value is on your sample because you only get one sample. If its variance is too big, then it could still be very far away from the mean, from the true value. So that's why we need to consider both bias and variance. And the good estimator, hopefully, is small in both. But in many cases, we have a trade-off. Okay, so the variance is defined as variance of beta hat. So again, we are going to put in the formula for beta hat, which is what we have here. It's the variance of x transpose x inverse x transpose y. Okay, again, here the only random vector is y. And to calculate this variance, because I would say it's actually a not so formal way to say it. Because in this case, beta hat is a p-dimensional random vector, right? It's a coefficient vector. So we should call this variance covariance matrix in the strict way. And some people may just call it covariance matrix. So in this case, how can we compute the variance covariance matrix? So to get this, and we know that what's random is y. And this will require some knowledge about this, how to say, do the calculation. We need some knowledge about how we can open up this variance. So just for your information, it is a fact that if we just make it more general, if we have a constant matrix A, which is like the same dimension as x transpose x inverse x transpose, and this will be p by n, okay? And the random vector y, which is n by 1. So the fact is that such variance covariance matrix can be written as A times the variance covariance matrix of y, which is n by m, times A transpose. Okay, so then you can see this is analogous to when you calculate the variance of a scalar random variable, for example, AY, right? So I'm just saying that if you have this variance of AYI, because now we are in the scalar case, this is equal to just A squared variance of YI. So this is a scalar case, this is the matrix case. Okay, and then coming back up to here, we just use this fact to do the calculation. And you can see that we will treat X transpose X inverse X transpose as our A. And we will get X transpose X inverse X transpose covariance matrix of Y and the inverse of this A. That turns out to be X times X transpose X inverse. Okay. So what is remaining is what is the variance covariance matrix of Y, as its randomness solely comes from epsilon. This is equal because X beta, that term in the matrix form of linear model, doesn't contribute to variance. So this is equal to variance of the epsilon vector. And based on our simple assumption, this turns out to be sigma squared times identity matrix of n dimensions. So then you can see identity matrix doesn't play any role in this product. It can go away. And sigma squared is a scalar. It can come to the front, right? So therefore, from here, this term itself, if I continue to write it, it can be written as sigma squared times X transpose X inverse X transpose continues with X times X transpose X inverse. Okay, and then you can see we can have one copy of X transpose X canceled with its own inverse. So we're left with sigma squared X transpose X inverse. Okay, so which is good, right? So this is what we get for the variance covariance matrix of beta hat under fixed design. If you are a little curious, what happens if we're under a random design? That is a good question, because in this case, we can actually leverage the fact that something called the law of total variance. So for the random design, so for fixed design, we're good because X transpose X inverse is fixed. But just for information, if you are interested in random design, then you can consider this decomposition, which is for the variance of beta hat. Now you can consider, but you must consider both X and epsilon together to be random, right? So in this case, we can use the fact of this law of total variance, that is expectation of the variance of beta hat conditional on X plus the variance of the conditional expectation of beta hat on X. Okay, so you can basically do this. And then what happens is that, so when you conditioning on X, you're basically like under the fixed design. So that's why the variance that beta had given X is what we just get from here. So it's just what we just derived, sigma square X transpose X inverse. Okay, and for this condition expectation is what we get from the bias part by treating X as fixed, okay? And that's basically beta. Has nothing to do with X. So therefore, you can see the second term is 0 because beta is not random and we're left with first term, okay? So therefore, under the random design, the covariance matrix for beta hat is expectation over what we have under the fixed design. So you're considering the possibilities that your design matrix can be different. Okay, so that's all I want to say for the variance part. And we have talked about bias variance for beta hat. Any questions before we continue? So again, as I said, the most important thing is to consider randomness. to think about what is the random vector in the whole model setup. Under fixed design, only epsilon is random. Under random design, both x and epsilon are random. But if you want to have some good result for a random design, it is essential to assume x to be independent of epsilon. Otherwise, the coefficient beta may not be so meaningful. That is the practical reason. Okay, so if we continue, we have another parameter to, so something I haven't said yet, but we'll postpone this a little bit. So besides the variance of bias and variance, the third property we are always interested in is distribution of beta hat. The reason we want to know this is because once we know the distribution of beta hat, we can use it to help us guess beta, right? Because if beta hat is something has a distribution like a Gaussian distribution concentrated with the mean on beta, then you know, yes, beta is not so far away from beta hat. So the distribution can help us infer beta from beta hat. So we can infer beta from beta hat. Beta hat is the value we observe. Okay, so we will postpone this a little bit before we and after we finish talking about another parameter. So these are for beta, but don't forget that in this linear model, I'll just write it again as a reminder. In this linear model, there's another parameter, sigma square, okay? So both beta and sigma square are parameters we need to specify the model. But we also know that beta is our parameter of interest because we do this modeling just to know the effects of our predictors, our features on the response. But what is sigma squared? It is something necessary to specify the error distribution, the model, right? The randomness where it comes from. So it's not so interesting, but it's necessary to be accounted for. So that's why the sigma square is called nuisance parameter. I think I mentioned that last time. Well, this beta is called parameter of interest. Okay, so how do we estimate this? The most straightforward way to think about it is to do MLE again. So you can still come back to the likelihood. So in the likelihood function here, even though we previously only focused on beta, and also you can see to maximize likelihood based on beta, there's nothing to do with sigma squared since they're not in the same term, right? So basically, I mean, in the numerator, you only have beta. So for any sigma value, once you want to maximize the likelihood by changing beta, you get the same solution. So that is the good thing. So estimating beta doesn't require our knowledge of sigma squared. But now let's come back to the likelihood function. If our focus is now for sigma squared, what can we do? So naturally, what you can do is that you can find a way to take derivative against sigma squared and then try to see whether you can set that to 0 to solve for the sigma squared. But something you have to bear in mind is that sigma squared's domain, the range of values it can take is not the whole real line. It's just it's actually just non-negative, right? Sigma squared is a non-negative value. So that's another thing we must consider when we try to find a value to optimize our sigma square, to optimize the likelihood. So I can just quickly say that basically we can show sigma square MLE has this form. So for sigma square by MLE, maximum likelihood estimation, it turns out to be, we just write sigma square hat, to be just 1 over m summation over observations yi minus xi transpose beta hat square. And the beta hat is what we just estimated, the OS or MLE. So then you can also see that for this one, this difference, actually we give a name for linear model or regression in practice. This term is often called residual. Okay, so we can write it as EI square, where each term before the square, the difference is called a residual EI. So you might recall that in my last lecture, I emphasized the difference between a residual and an error term. And here it is again. So EI, the residual, relies on our model fitting and is based on our observed data. Basically, it is something we can see. But the error term epsilon I is something we never see, we never observe. It is what we assume to be the random error term or random variable in our model. So epsilon I is imaginary, while EI is something we achieve, we concretize. Okay, so for simplicity, we can also put E1 to En just like epsilon 1 to epsilon n in the vector form. So we can denote E as a vector to be E1 to En, all right? And then you can see this E can be naturally written as in the vector form, just as Y minus X beta hat. Okay. And furthermore, we can plug in the formula for beta hat, which is, if you still recall, X transpose X inverse X transpose Y. Now, both terms are just based on Y, based on the response. And we can combine them into one term. We can write it as identity matrix, which is n-dimensional, minus X transpose X inverse X transpose times Y. Okay, this is the residual vector formula. And you might have noticed that we have written this X times X transpose X inverse times X transpose twice, right? At least for the notation simplicity, we should give it a notation instead of just writing it out every time. And also you can notice that this has a very good symmetry. And we call this actually H. And in the linear model literature, it has a name called hat matrix. So when people say hat matrix, they mean this. And it is n by n. Okay, so therefore you can see essentially with this notation, then E is identity minus hat matrix times Y. And hat matrix is something we can play with in the, how to say, when we do derivation. Because if you write H, right, it's short. And also H has some nice property we can make use of. So I'll just quickly say some nice properties of H. I think this is something like a mathematical fun fact from the linear modeling. And I would say these fun facts are very useful and essential when we needed to do hand calculation in the old days, right? So we have to simplify our calculation as much as possible. And sometimes I have this thought that with the development advances in our technologies like computer, sometimes we tend to think less because we can easily use the technology to do things for us. While in the old days, with so little tools at hand, we have to think more to make it possible. So that's an interesting contrast. So for properties of H, first one, it's symmetric. So you know that as a symmetric matrix, its transpose is itself. This can be easily verified. You can just do the transpose of this. Yeah, and not just that, but I minus H is also symmetric by nature. So that's a nice property. And the second property, this one has a name called idempotent. So what this means is that the square of h is just h. So once you take a square of it, you're staying the same. Okay, and this is very similar to the scalar 1, right? Square of 1 is still 1. And I minus h squared is still I minus h, which is also very nice. And the third property, which is nice about h, is its trace. What is a trace of a matrix? It's the sum of the diagonal entries. Okay, so here we can show that using a nice property of trace itself, which is basically you can do it in a circular way, right? Where you keep the order of the product, but you can always move a thing to the front. So what I'm saying is that if you calculate the trace of h, which is this, what I can do is I can move the last one to become the first one. And then the trace is kept. And this is a property of the trace. So it's equal to x transpose x times x transpose x inverse. Okay? And then now you can see I have cancellation. Well, after the cancellation, I get an identity matrix. And the dimension should be p by p. So basically, it's a trace of an identity p-dimensional matrix. And obviously, its trace is p. So H has a trace of p. And then I can easily show that for I minus H, because I here is n-dimensional, it's an n-dimensional identity matrix in here, because everything is n-dimensional. I just put n here for clarity. And this one will directly give me a trace of n minus p. Okay, this is something very important in our understanding of the degree of freedom for our residuals. Okay, so now I'm going to do a contrast because we have E, I'm writing it down here, as equal to I minus H times Y. Okay, this is the E vector, residual vector, versus epsilon, which is the error term, error vector. So what I'm trying to say is that if we think about their degrees of freedom, E has n minus p, while epsilon has a degree of freedom of n. So I know some people may think degree of freedom is a very abstract concept, but how do we make sense of it? I would say the most easy way, in my opinion, or based on my learning experience, is to think about sampling, the sampling process. So what this means is that if you sample your error terms, epsilon 1 to epsilon n, they can be totally unrelated, right? Each one's value can be unrelated to the rest. That's why we say they are IID, independent. So therefore, the n degrees of freedom reflects that total independence. While here, for E, you don't really have that independence. The reason is because basically, even though Y, okay, n-dimensional vector, as a result of epsilon, y1 to yn has n degrees of freedom because the fixed part, x beta, you can ignore it. You just think about the variability from the random part, epsilon. So the 1y to yn has n degrees of freedom. But this degrees of freedom is basically constrained, reduced by this left multiplication. And the left multiplication is because for this one, if you just multiply by I, okay, I identity matrix, it has trace n, and I times y is still y. So you don't lose any degrees of freedom. But what you multiply is not just I, but I minus h. And I minus h has a less degrees of freedom reflected by the trace. Now it's reduced to n minus p. So in other words, you lose this degrees of freedom by this left multiplication. And also it makes sense because you can see that for between two residuals, E1, E2 to En, here, the residuals are not independent of each other. The reason is because they rely on otherwise. So each EI is calculated based on otherwise, not just one Y. So therefore, the dependence, so therefore they become dependent, right? So you are not just relying on its own thing. So if you think about the vector form here for each EI, basically it's yi minus the ith row of H matrix times the whole Y vector. So that's why it involves the whole Y. So this dependence between residuals is another reason why I said it's very important to distinguish residuals from errors. Okay, so I want to say that E1 to En are not independent. This is very important message. Okay, because each EI, I'll just write it out, is basically Yi minus the ith row of hat matrix. Maybe I'll just write it as Hi transpose times Y. Okay, so if I just write it, the hat matrix as H1 transpose to Hn transpose. So that's it. Okay, one more thing is that once we get the estimator, back to the estimator, sigma square, which is 1 over n sum ei squared, right? We can also write it as 1 over n e transpose e in the inner product form. So the question we want to ask is also similar. Is it unbiased? What is its distribution? So we can also ask similar questions. So to answer the bias question, we can take expectation. Okay, so now it becomes, how do we take expectation of sigma hat square? And it's not so easy because we have the square of EIs and we need to basically do, if you want to go back here. Okay, if you want to use this E formula, I minus H times Y. So basically you need something like the square for Y, quadratic form for Y. So that is, you have 1 over n E transpose E, right? Even though I can do the plugging, I'm just doing a few steps. So I minus H times Y, that's E. So I do the transpose, Y transpose, I minus H because it's itself, times I minus H times Y. Okay, then the idempotent thing will help me because this thing, I minus H times minus H, is still I minus H. So I'm getting 1 over m expectation of Y times I minus Y transpose times I minus H times Y. Okay, this is what I need to get to the variance, to the bias. And then here, we also need to know expectation of Y transpose Y. Okay, so that's something we haven't calculated before. So one thing I can directly tell you as a result, instead of doing the full derivation, even though it's possible, you can do it. But I think for the purpose of this class, I think intuition is more important, that I'll share with you a very important result that can quickly, it's like a shortcut that can get us to this result. That is, we can actually derive distribution for the residual sum squares. That is, we can actually show that. So with the condition or assumption, we previously assumed that epsilon is normal 0 sigma square Im. So with this assumption, we can actually show this sum of ei square, I from 1 to n, if we divide it by sigma squared. This can be regarded as a normalization to remove the effect of sigma squared. This can follow chi-square distribution with n minus p degrees of freedom. So I'm trying to introduce this result because we just talked about degrees of freedom and it can be reflected here. Well, if you're familiar with the derivation of chi-square distribution, you know, this is something we used to cover in the undergraduate class. For chi-square distribution, it is very simple to be derived as or defined as if you have z1 to zn IID standard Gaussian random variables, then the sum of zi square, I from 1 to n, follows chi-square distribution with n degrees of freedom. So this is the definition of chi-square distribution. So you can interpret the chi-square distribution as a manually created distribution for simplicity. Again, it's in the old days. It was in the old days when people had to rely on manual calculation to get some, how to say, quantiles for chi-square distribution, for standard normal distribution. Then when they need to do any statistical analysis, they look up the table, right? That is still sometimes in our undergraduate teaching, even though that seems a little, I would say, outdated given the computer. But the introduction of such standard distributions is to enable such calculation. That's why we have them. But with the chi-square distribution, you can see the way defined is the sum of standard normal squares. And how many independent standard normals you have, the degrees of freedom, is the degrees of freedom of the chi-square. So as I said that E1 to En only have n minus p degrees of freedom. That's also reflected in this distribution. Okay, and also based on this definition of chi-square, you can easily see that if I do the sum of epsilon I square, I from 1 to n, the random variables in my model divide by sigma square. This is just to standardize each epsilon I to be a standard normal. That will follow chi-square distribution with n degrees of freedom. So in this comparison, you can also see that the residuals are different from the error terms. Okay, assuming that we know this knowledge, and starting from here, chi-square has a very good property. That is, so if you know those standard distributions properties, you can save time. Its expectation of chi-square random variable, degree freedom n, is just n, okay? And the variance is 2 times n. So if you know this property for chi-square, then you can immediately use this result to say, based on that, I can have expectation of the sum of EI square to be equal to sigma square multiplied by m minus p. I skipped one step by doing the multiplication on both sides for sigma square. So you see, and then we want to ask for the bias question, because for the sigma square hat, it's defined as 1 over n times the sum. Okay? And then you can clearly see it will become sigma squared times n minus p divided by n. Unfortunately, it's not equal to sigma squared. So in this case, we will say the MLE defined as this is not unbiased. It's actually biased, okay? But it's just that if we do the bias calculation, it's just the bias, it's a small thing. It's basically sigma squared times n minus p divided by n minus sigma squared. So the expectation minus the true value. And we can clearly see that it's just what? It's basically just minus p over n times sigma squared. So in the classical setting, again, this is important. We are considering p to be less than n, p fixed. So we have predefined our predictors. And the predictor number will not increase as our sample size increase. So in this case, you can see that p fixed, only n increases. This will go down to 0 as n increases. So that's why this bias is called asymptotically 0. Or we can say the MLE estimator is asymptotically biased. When n goes to infinity, it's unbiased. It's asymptotically unbiased. But if you are having a finite sample, that is n is finite, it is biased. So that's another thing. And furthermore, with this formula, with the expectation calculated, we can easily create another estimator that's unbiased for estimating sigma squared, which is straightforward. So the unbiased, finite sample unbiased estimator can simply be defined as sigma squared. Maybe I'll just write unbiased here for information. Can be simply defined as 1 over n minus p instead of 1 over m times the sum of residual square. If you define it that way, then you can immediately have an unbiased estimator. Okay, and I think I basically try to provide the justification of why in some software packages, you would have sigma square estimated using this denominator, n minus p, instead of m. But I think it might differ sometimes from function to function. So make sure that you know which one you're using. But if your n is very large compared to p, their difference is negligible, right? Doesn't matter that much. But if your n is small, then it becomes more important whether you want to have the unbiased estimator. Okay, any questions for now? We basically introduced how to do the bias calculation for estimating the sigma square variance for error terms. Okay, now we want to introduce some terminologies. One is this, sum of residual squares. So this is another thing I think clarification is needed because people may see different ways of calling this term in different contexts. So in many books, this term is called RSS, stands for residual sum of squares. But in the context of ANOVA, which we will introduce in this class, ANOVA is basically a technique to decompose the variance of Y response into two parts, the variance that can be explained by the model by X beta, and the variance that cannot be explained by the model, the random error variance. Okay, so ANOVA is analysis of variance. So that's what it stands for. So in ANOVA, this term is referred to as SSE. So it stands for sum of squared errors. So I would say probably RSS is what I prefer because they're the residual. But in SSE, it's called squared errors. That can be somewhat confusing because we have the error term, right? So we have the error term as the random variable, the epsilon. But still, that's what it is. It's in the literature. So when you see RSS or SSE, they both mean sum of residual squares. Okay, so coming back to distribution of beta hat. So the reason why we need this is because, don't forget, in our variance calculation for beta hat, under the fixed design. So look at this line. This is where we are at, right? Variance, covariance matrix of beta hat is equal to this sigma square x transpose x inverse. This is the important thing to pay attention to. But you see that even we do this calculation for the variance, covariance matrix of beta hat, we cannot calculate it. The reason is that sigma square is involved. Even though we observe x design matrix, but we don't observe sigma square. But now, if we have an unbiased estimate for sigma square, we call that sigma square hat, we can plug that in, and now we can have an estimate of the variance covariance matrix of beta hat. So what I'm saying is that this covariance matrix itself has unknown parameter involved, sigma square. But if we do plug in sigma square hat, we can get an estimate for the variance covariance matrix of beta hat, and we can call that sigma square hat x transpose x inverse. Okay, so this has become something we can calculate from our data. Okay, now finally, property 3, distribution of beta hat. How can we find an approximate distribution for beta hat? Because I would say this is an estimator for variance covariance matrix. So how well it approximates this variance depends on how good this sigma square hat is an estimator for sigma square. So that carries over. So it can be unbiased. We can make it unbiased, but it itself carries with randomness, with variance. So on a particular data set, maybe when n is small, so this value could still be quite different from the true value, and that would affect everything. So I just want to bring this to your attention, that with only one data set, there's only that much we can say, especially when your n is small, an unbiased estimator could still carry a value that's far away from the true value. Okay, so for distribution of beta hat, I'll quickly wrap up here and continue next time on Monday. I apologize for the delay in the beginning due to the technology I didn't figure out. But I will say that as an ending here, I hope to say we have a very good asymptotic distribution for this beta hat coefficient estimate vector. So asymptotically, we can have beta hat minus the true value beta multiplied by square root of n. So this is a very standard way of writing asymptotic distribution in statistics. Well, I'll tell you why. So I will say that this approaches in distribution to this p-dimensional normal distribution. Okay, p-dimensional normal distribution. I'll just write p here with a 0 mean vector, okay, and a covariance term. But for this covariance term, I will not specifically write it out for now because I'll tell you it's not directly the sigma square times x transpose x inverse, because this one because x as a design matrix has n rows, so there is n involved in this formula. And I would say if we just look at the variance of beta hat, this one, we can show that it will go down to zeros. Will go down to 0 as your n goes to infinity. So going down to 0 means that all the variances become negligible so that the estimate become not random. So it will not be random around its true value anymore. So therefore, to get a distribution that doesn't shrink, because otherwise the larger the n, the more concentrated beta hat will be on beta, so you will have a shrinking distribution, and that distribution will shrink to 0, a point mass, so you cannot use it to say anything. So this factor root n is there to protect the distribution from shrinking, or from, how to say, collapsing. It will make sure that it is a stable distribution so that on the right-hand side, the terms will not evolve n. Sample size will not be on the right-hand side. It will only be on the left-hand side because we are saying as n goes to infinity. So this is a limit that doesn't depend on n. So I hope this makes sense. So the reason we want to use this asymptotic distribution is that with this, we can do some calculation to get, for example, a confidence interval for our beta j based on beta hat j. So we can say something about what we believe to be the true predictor effect size given the data. Okay, so that's what I want to say today. And we won't have any homework for this week because we just started. And I'll see you on Monday. I'll see you on Monday in person.
Thank you.
Bye, everyone.